if there is any problem with the slides, and please, during the talk, feel free to interrupt at any time to ask any sort of questions. I'd like this to be a kind of interactive talk, so I encourage you to ask and to interrupt me. I also so I shall say that I want to cover a lot of ground with this talk without going too much into detail, because I want to kind of describe a whole whole setting, a whole scenario that and kind what led me to my PhD research. So I'm going to talk about complete internal categories, and I'd like to start by, as a way to give a little bit of context, to talk about small complete categories. So one could wish to have a category that is both small and complete, because smallness, since if we have a small category, so we have no size issues, there are some very interesting results we can prove. For example, that completeness and co-completeness are equivalent notions. So like a complete category will automatically be co-complete, which is of course not true for a non-small category. And a classic result such as the adjoint functor theorem is, of course, it holds, but it holds without the solution set condition, which is a set theoretic condition that is precisely used in the classical version of this theorem to control size issues. And unfortunately, it is an unpublished result by Freyd that if a category is small and complete, then necessarily it is a complete preorder. So this is very disappointing, because it means that our examples of small complete categories, I mean, there are very few of those. There are very special examples, and they're not the kind of categories we might want to work with, because they're categories where between two objects there is at most one arrow. So we may notice that a small category, we might remember that a small category is nothing else than an internal category in the category of set. And so the idea is that we look into internal category theory to find a solution to this issue of we want small and complete categories, but there are not enough of them. So as a reminder, an internal category requires to have an ambient category with at least finite limits. And then we define an internal category by a diagram having an object of object and an object of arrows, and then a structure analogous to the usual structure of categories. So we want a source and target for the arrows. We want an identity arrow for every object, and we want composition of consecutive arrows. And these have to satisfy kind of usual associativity and unit axioms that are precisely the translation in the internal language of the ambient category of the usual axioms for categories. Analogously, we can define functors that are given by an action on object and an action on arrows. I just spot a typo here. The functor should go from a category A to a category B, not necessarily be an endo functor. And this has to satisfy functoriality axioms. Now, bear with me, we still have natural transformations, which again are, just what we would expect. They are families of arrows indexed by objects and satisfying naturality axiom. So with all this data, we get a two category of internal categories in E, given by the internal categories, their functors, and natural transformations between them. So if the ambient category furthermore is locally Cartesian closed, then we get that the category of internal categories is Cartesian closed. So we get, like this shows that we get a nice theory of internal categories. And under this assumption that the ambient category is Cartesian closed, we can define completeness. So a cone for a diagram that is a functor, an internal functor over our targeting our category, will be given by a vertex and like the components of the cone. And we need the Cartesian closed structure to define this, because we need the exponential transpose of the diagram. We also need a delta functor that intuitively takes an object of A and returns the constant functor on that object. But otherwise, like if we forget for a moment of being the internal context, this is the usual definition of a cone. Where things get tricky is the definition of limit. So we would expect that a cone is universal if it is terminal among cones over the diagram. But this is not enough, because we want the definition to be stable under pullbacks, so that it will have sense in the internal language of the category. And for that, we need to explicitly require that the cone is terminal in every slice for every slice of the ambient category. And then, again, similarly, we would expect a category to be complete if every diagram admits a limit. But again, this is not enough because it's not stable under pullback. So we want we want to have the limits for every diagram in every slice of the ambient category. So we force the definition to be stable under pullback. And this definition, which is forced to be stable under pullback, is called strong completeness, as opposed to a weaker form of completeness that is not, like, makes sense in the from the external point of view, but is not stable under pullback, and so it doesn't make much sense from the point of view of the internal language of the ambient category. So if we have a complete internal category, we retrieve those results that we liked about small complete categories. That is, a complete internal category will also be co-complete, and there is an adjoint functor theorem that holds without assuming any extra condition, such as the solution set condition. So far, this setting looks very promising, but there are a couple of outstanding issues. The first is that, well, first of all, we want examples of such complete internal categories, because of course we have the examples of the internal categories in the category of set, that is small and complete categories, but we already saw that these categories here can only be kind of degenerate, can only be partial preorders. And so we need to find a new setting different from the category of set, in which there are interesting complete internal categories. The other outstanding issue is that internal category, like internal category theory is not very expressive. For example, we cannot express the Unedal lemma. That is because there is no internal equivalent of the category of sets. So there is no hope to get a category of presheaves. And more essentially, the fundamental reason is that the Unedal lemma naturally lives in the enriched context. So we need we have the Unedal lemma when we consider a category to be enriched over set, and then we have home set. Analogously, we have a generalization for enriched categories. And so the idea would be to have an equivalent, an analogous notion of enrichment, but in the internal setting. And this is what I've been working on during my PhD research. So is it all good so far? Can you still hear me all right?
Yeah, no problem.
Yes, no problem at all.
Okay, all right. Okay, so if there aren't any questions, I will now I will go through like these two issues like one after the other. So the rest of the talk will be split into these two parts. So our first goal is to construct an example of an interesting complete internal category. And that is provided by the classical example of this is the category of model sets as an internal category of the effective topos. Now, I will quickly remind you what realizability is. The idea is to have a semantics for a predicate calculus in a non-standard set of truth values, in a set of non-standard truth values. So we take the power set of the natural number as our set of non-standard truth values, meaning truth values will not be true and false, but will be subset of natural numbers. And a predicate on a set, a non-standard predicate on a set will be a function from this set to the set of non-standard truth values. And then we can define a semantics for our predicates, in which fundamentally, instead of just tracking the values of the classical values of truth of our predicates, we track kind of witnesses that these predicates are true. So we say that a number realizes a predicate when this number belongs to the set identified by the non-standard predicate over a certain element. And we say that a predicate is valid if it is uniformly realized. So if it has a number realizing it for every possible value of x. So this gives us a form of constructive logic, and we can use that to define the effective topos. So the objects will be a pair given by a set and a non-standard equality predicate. So where this equality predicate has to satisfy symmetry and transitivity, although currently not reflexivity, and to satisfy in the sense that the symmetry and transitivity predicates are valid in the realizability sense. Analogously, we define morphisms as non-standard functional relations. So we have a predicate that has to satisfy all of these properties, and we identify two of these functional relations when they are that there is a by implication between them. So with this data, we get this data form a category, of course, but this category turns out to be a topos and not a Grothendieck one. That is a fundamental point, because in a Grothendieck topos, we can replicate the argument that internal complete categories are partial preorders. So if we want a more interesting example, we necessarily need to place ourselves in a setting which is not a Grothendieck topos. Now, there are special objects inside the effective topos. The assemblies are objects in which if there is a witness that two elements are equal, then these elements are actually the same in the underlying set. We call these object assemblies, and these form that identify a full subcategory inside the effective topos. Then we have model sets which satisfy these three conditions. And the idea about model set is that they are completely realizable objects. So inside the effective topos, you can just import a set with, you can embed a set which will behave as a standard set theoretic set. Allow me the pun. And but model sets have a behavior which is entirely given by their non-standard predicate. So if for every element of the underlying set, there has to be a witness that this element is equal to itself, and when to be equal to itself, we say that it is a proof that the element exists. So we say that an element exists if there is a witness that it's equal to itself. And then we have that if there is a common witness that an element X exists and that an element X prime exists, then these elements X and X prime have to be the same. And moreover, the set of realizers that X is equal to X prime is given by the intersection of the realizers that X exists and X prime exists. So even though, the first remark is that a model set is, in particular, is an assembly. It can be deduced by its properties. So we have this hierarchy of objects inside effective topos: generic objects, assemblies, and then model sets. Moreover, a model set is, even though we define it as having an underlying set, because every element of the model set has to be realized by at least one realizer that is not used by any other element, then it can have at most a countable number of elements. And these elements are kind of identify equivalence classes over the set of natural numbers. So a model set can equivalently be seen as given by a partial equivalence relation on natural numbers. This means that we can embed internally to the effective topos, we can construct a category of model sets. So model set is both, like we both have a subcategory of the effective topos that is given by model set, but we also have an internal category in the effective topos representing model sets. And actually, this internal category of effective topos also lives, this internal category of model sets also live in the category of assemblies. So it is a classical result of Island that the category of model sets is weakly complete in the effective topos and strongly complete in the category of assemblies. The distinction between weak and strong completeness is the one I was referring before, like regarding the stability under pullback. For our purposes, we are only interested in the strong completeness. So our example will be actually that of the internal category of model sets inside the category of assemblies. And the category of model sets is definitely a non-trivial example in the sense that it's not a partial pre-order. So it provides us with this example of a small, interesting, small and complete category, which we could not have in the set setting. And we still have the other outstanding issue, that is internal category theory is not very expressive because we lack a notion of enrichment. And I will now go on showing that we can define a notion of enrichment internally, like an internal notion of enrichment, and this will preserve all of the good properties of internal categories with respect to completeness. So our setting will be that we have an ambient category with finite limits. We will later require also this category to be locally Cartesian closed. And we need an internal monoidal category. That is an internal category with a monoidal structure given by internal functors and natural transformations. Then we define a category enriched in the monoidal category V as given by an object of E of the ambient category and equipped with a home set, a composition, and an identity, where the composition and the identity have the expected signature if we write them in the internal language. So if you interpret the signature of the identity and the composition in the internal language, you get these arrows, which are what you would expect in standard enriched category theory. And this structure has to satisfy associativity and unit laws. And here we have the axioms, which are precisely the same diagrams we have in standard enriched category theory, but have to be interpreted in the internal language. So all of these diagrams live inside the ambient category E. But we can make perfect sense of commutative diagrams in the internal setting. So this is not an issue. And of course, we can define functors as expected, given by an action on objects and an action on morphisms. where the actionomorphisms act on the home set of the source and target category, and this has to satisfy the functoriality axioms. Here we have one of the functoriality axioms saying that the functor preserves composition. And we can define a composition of functors in the usual way by composition of the object component and composition of the arrow component. So the whole point of this is that if we, the fundamental catch is that if we work in the internal language of our ambient category, we can actually replicate pretty easily all of the constructions of standard enriched category theory. So this is all very nice and clean. We also have natural transformations, which again are given by a family of arrows indexed by objects, and that this family has to satisfy a naturality axiom. So with all this data, we have two requirements for this proposed theory of internal enrichment. The first is that the theory itself is nice, so that for example, that internal enriched categories form a category which is monoidal. I would say Cartesian closed, but actually if we have a monoidal product, so it will have to be monoidal closed, and that this theory is expressive enough to express the Unit dilemma, and that it is also well behaved with respect to limits and completeness. And then we will have a kind of setting which satisfies all of our requirements and successfully put together the internal category theory and the enriched category theory. So yes, we also have a definition of the various kinds of compositions of natural transformations. I don't want to spend more time on these. So if we can see that V categories, V functors, and V natural transformations form a two category, and that if the enriching category V is symmetric monoidal, then the category of V categories is symmetric monoidal as well. And it has to be noticed that it is not true that if the enriching category is monoidal, the enriching category is monoidal by itself, that doesn't suffice to show that the category of V categories is monoidal, because we really need symmetry to define the monoidal structure. But this shouldn't come as a surprise, because it is perfectly analogous to what happens in standard enriched category theory. So if then assuming that V is symmetric monoidal, and also assuming that the ambient category is Cartesian closed, we can prove that the category of V categories is enriched over the category of internal categories, which is a first step towards showing that the category of V categories is monoidal closed. And fundamentally, this consists in taking two enriched categories and constructing an internal category in E given by an object representing the functors between X and Y, and an object representing natural transformations between X and Y. And this is again, possible because the internal language, where now at this point is the internal language of a locally Cartesian closed category, is expressive enough to construct these objects, to kind of internalize the definition of functors and natural transformations. So to get any further, we need to assume that our enriching category is monoidal closed itself. And we need to give an internal definition of monoidal closedness, which is the usual existence of adjoint functors. And again, as it is true in the standard setting of enriched categories, if our enriching category is monoidal closed, then it has an enrichment over itself given by the monoidal closed structure. So we now gather all of our assumptions. We need that this symmetric monoidal closed category is complete in the internal sense and also has equalizers. And this is a curious thing to notice, that an internal category might be complete and not have equalizers. And that is because an equalizer means that two arrows have an equalizer, and the ambient category might not know about the concept of two, because we never required it to have colimits. So I'm not aware of an example of a suitable setting for such constructions which doesn't have the colimit 1+1, but we need to be careful, and we need to then assume in general that there are equalizers as given by an abstract definition. In most situations, these will be implied by the completeness of V plus the existence of the colimits in the ambient category. So if we have all of these assumptions, and again, the ambient category is locally Cartesian closed, then the category of the enriched categories is itself monoidal closed. And the reason, the way we prove this is by replicating the standard proof for this fact in enriched category theory, which uses coends and the coend formula for natural transformations. So the set of natural transformations can be described by a coend, and in this case, we use that to produce our home objects.
Sorry, Enrico, there is one question from the audience. Jonas Frey is asking, who is ECAT, eternal category?
Sorry, Ivan, I cannot hear you very well. It's very robotic.
Okay, can someone else speak instead of maybe Fosco?
Yes.
I can sorry, yeah. Maybe that's easier. Sorry, that was 3 slides back. I think you said that sorry, I forgot the statement. Can you?
How is cat E an internal category?
You said V cat E is enriched over cat E, but so that's an external enrichment statement probably, or is it?
Yes, absolutely. So VCat is an external category, and it's not. I'm not going to internalize that. And cat E is an external category. So yes, this is a plain old, good old enrichment. No internal nonsense here. But
okay.
the construction, of course, of the object of functors and the object of natural transformations, that has to be internalized.
Yes, yes. Okay, sorry for that. Yeah, I only noticed the solution now that you showed the slide again. Thank you.
Thank you very much, Jonas. Are there other questions since we're here? Okay, then I will keep going, but again, feel free to interrupt me any time. We have that the category of V categories is monoidal closed, and I should specify is monoidal closed as a standard external monoidal category. So this is not about the internal monoidal closedness of V, but this is enough to express the Yoneda lemma. So we need to express it in a form that is slightly unusual, but if you kind of read between the lines, you will see that it states the usual statement of the Yoneda lemma, that is that the home set of the Yoneda embedding is retrieves the action on a functor. So far we have shown that the theory of internal enriched categories is a well-behaved theory in the sense that the category of V enriched categories is monoidal closed, and it is also expressive in the sense that it allows us to express the Yoneda lemma. And of course, the Yoneda lemma, we take it as a kind of example of something that we really want. Of course, there are also other results that we expect, and these also hold. So the theory does not present nasty surprises. What we still have to do is to look at its behavior with respect to completeness, and see that it is actually well behaved in the way that internal category theory is. So for completeness, we define weighted limits for any functor and any weight as given by a natural isomorphism, and we say that a category, an internally enriched category is complete if it has all limits in every slice of the ambient category. So again, we need to enforce stability under pullback. And this formulation of weighted limit is the usual one from enriched category theory, and we have all the structure we need to express it now, because we have a monoidal closeness, so we have the home of an exponential category given by the category of functors from K to V. So everything is in place. And the nice thing about this definition of completeness is that it can be shown that it implies it produces a limit functor. So a choice, like a functorial choice of limit given a diagram as a weight. in the sense that the definition of completeness requires, the existence of certain limits, but it is an externally produced existence. One might suspect that there is no way to internalize this existence in the category, but actually this is possible, and you can get an internal functor which produces all of these limits. And this is also true for the notion of strong completeness for internal categories. So this is kind of the proof that the notion of completeness is the right one. It's strong enough to produce an internal choice of limits. And we noticed that V was complete as an internal category. It was also enriched over itself because it was monoidal closed. And we can then show that it is complete as a V category. So the notion, like the internal notion of completeness is carried to the enriched context and becomes like completeness over weighted limits. So we also notice that if a category is complete, then the category of functors targeting it is also a complete category, which in particular means that the category of presheaves are complete, which of course is something that we really need. Since we want to state the adjoint functor theorem, we need a notion of limit preserving functor, which I call continuous because all limits are small in this setting. So we say that a functor is continuous if it preserves limits, but not just all limits in the ambient category, but in every of its slices, because again, we have to enforce stability under pullback. And as a fundamental lemma, we need that if we have a covariant presheaf, which is continuous, it preserves limits, and such that its weighted limit weighted by the identity functor exists, then this weighted limit actually represents the functor. And with this result, we can easily show that if an internally enriched category is complete, then it is also co-complete, because we can take a functor, like given a diagram and a co-weight, we can construct a functor f, which is fundamentally the right-hand side of the isomorphism we seek to show that the colimit exists. And then using the previous theorem, this functor f preserves limits, so it is representable and by this limit, and this limit satisfies the property that defines the colimit. So we have that the colimit of G and W is given by the limit of F weighted by the identity. And so this shows that every colimit can be obtained by a limit. And with similar techniques, we can show the adjoint functors theorem. So again, we have that if we have a continuous functor whose domain is a complete category, then this is a right adjoint, and there is no need for any solution set condition. As notable consequences of this, we have that categories of precis are co-complete, and that if we have a complete category, then the Untitled embedding of this category is a right adjoint. So to sum up, what I try to show is that we would like to work, fundamentally, we would like to work with small complete categories because they have very nice properties with respect to completeness. But in the set environment, these are only kind of degenerate examples of complete partial preorders, complete preorders. And so we first think of working with internal categories, which indeed present interesting examples of complete internal categories, which behave nicely in the way that small complete categories do. But the theory of internal categories is quite limited. So we make it more expressive by introducing internal enrichment. And at the cost of some technical development, this gives us both the expressivity and the good behavior with respect to complete limits and completeness. And so this is a very neat setting in which things that will not be usually possible or would be very complicated can be obtained very easily and without kind of side conditions. And this is what I wanted to tell you. Thank you very much.
Enrico. Thanks. So I guess we can thank the speaker. And if you have questions, just chime in and ask them. If nobody has a question, I might have a question. I think there is a relation between your work and, I was struck by the fact that there is no Untitled lemma in this internal category theory in full generality. Yet I know that there are very many ways to fake the presence of an object that plays the role of sets in internal category theory. For example, there is the old work by Street in Elementary Cosmoi, or a more recent paper by Schulman, where he manages to reunite the enriched framework with the indexed or fibered category theory framework. So I was wondering if there is a relation between your work and these other attempts to... I remember that Schulman proves a form of Untitled lemma using internal profunctors in internal category theory. And he devises a notion of continuity that makes the Untitled embedding continuous. So I think there is a relation.
So there is totally a relation, and thank you for asking. This is I'm very happy about this question. Actually, I know of the work of Schulman, and I didn't talk about that, but so he presents various notions of enriched and fibered enriched categories. And these notions are connected to the notion of internally enriched categories by the externalization of internal categories. So if you have, when you have your internal enriching category, you can externalize it by producing an external category that is fibered over the ambient category, and then you can see that the notion of enrichment over these fiber category is fundamentally very closely related to the notion of enrichment, of internal enrichment in the internal category.
I see.
And it actually turns out that by doing these, internal enriched categories are a special kind of enriched categories over a vibration. So they are kind of a subset of the notion that Schulman studies.
I see. Okay, thank you. So, if there are there any other questions?
I have a question.
Yes, go ahead.
It's Jacopo. Hello, Enrico. So it's actually related to type theory, because as far as I understood, your ambient category is have to be locally Cartesian closed. And as you may know, the like extensional type theory can be seen as the internal language for this sort of categories. So I was wondering if you have thoughts about the possible connections between this notion of internal categories and enriched internal categories and the formulation of like the definition of a category that you can have in type theory, I guess in the essentially algebraic way, and then the possible definition of a enriched category in extensional type theory.
All right.
And maybe if the results that you have proven, if they also hold for the categories formulated in extensional type theory.
Okay. So I've not thought specifically about the definition in type theory, even though I guess you could say that the current definition is kind of a definition in the type theory of the internal language of the category, because it is given by formulas of the internal category. But there is, I think the biggest difficulty here, let me get to the slide, is the fact that the notion of completeness, both for enriched categories and internal categories, is not completely internalizable. So it still relies on universal quantifications and existence kind of outside
of the
ambient category.
I see.
And
yeah, that's a problem indeed.
Yeah, it is impossible, I think.
Oh, okay. All right.
I have also one question, Enrico. Thank you very much for your talk. I would like, I don't know if you can explain why in the effective topos there is an internal complete category. So do you have, if there is any abstract explanation for it? Because this how to produce new ones, let's say, okay.
I'm afraid I don't have a very deep explanation of why why like it works, like these things work in the effective topos. What I know is that like it is essential that the effective topos is not a Grothendieck topos. Otherwise, we might have like internal complete categories, but they would be kind of trivial. And so I suspect that the example of the effective topos can be generalized to other realizability toposes. So I think the setting of realizability toposes is the right one where to look for these kind of special internal complete categories that are also rich and interesting. But yes, that's what I know. But it is a I think it's a very interesting but also difficult question. So like it's probably not well understood at the moment why what like all the implications of these contexts.
I think it's related with impredicativity, and that's what puzzled me. Okay.
I think it's a good idea to expand more on this question in the free discussion later. I'm afraid we cannot go too much over time, but Millie was an interesting question, so thank you. So I guess we can just thank the speaker again, and